Good morning. So, start with why we need electric vehicles. We have a lot of government plan, got lot of government initiatives. Right now, ministries are doing a lot in terms of electric vehicles. We have a lot of policies, uh, e-mobility mission, and related other policies. Okay, I'll discuss about that to those also. Basically, it's not only a national electric mobility mission, but also we have a several initiatives which are directly or indirectly contributing to the national electric mobility mission. So first of all, just to begin with, why we need electric vehicles. So a clean alternative, cost saving, domestic energy independence, cheaper to run, cheaper to maintain, health benefits. So I'll come to one by one, basically, that what are the advantage or why we need electric vehicles. Now, a few points are there. India has decided, or as per the policy norms, after March 31st, 2023, three-wheelers sold in the country should be electric one only. After March 31st, 2025, it is proposed that two-wheeler below the capacity of 150 cc sold in the country should be electric ones. In 2017, Indian government posed the major policy of selling at least 6 to 7 million electric vehicles in India by 2020. And they are planning to sell only electric vehicle by 2030. So under National Electric Mobility Mission Plan by 2030, we are planning to have all electric vehicles, all vehicles as electric vehicles, we can say. So domestic policy goals, reduce dependence on foreign oil. Basically, we are exporting around 90% of our requirement. Although, second point, job creation. When we have a manufacturing units of electric vehicles and all, job creation will be there. Economic growth as well as related with that. Global impact. We are talking a lot of things about the climate changes and other issues regarding environment, energy dependence, independence, local energy sources reduce. So ultimately, we don't know how long this oils and those crude oil will go. So we are talking about some alternative. And interestingly, you will find that the Gulf countries, they are not bothering about those kind of research, or even they want that those research should not be conducted. Ultimately, it relates with their bread and butter. Since they are the, exporter of this crude oil, so they don't want that their shop should be shut down. But ultimately, a lot of research is going on worldwide. So I'll let you know what exactly people are doing in that area. So further, moving ahead, basically, right now you can see in the news that we are talking a lot about the air quality index, basically. So this is good when this is in the range of 0 to 50. But you might have seen sometime, even I was in Delhi as a student of IIT Delhi and even a frequent visitor for some meetings and all. So ultimately, at one point, it was 900. The AQI index was 900 in Delhi. Okay, this is not totally contributed due to the vehicle pollution, but some other factors are also there. But yes, still we will say that a major part of this AQI index is related with the vehicle pollution, basically. Okay, and these are the range. Severe range is 400 to 500. That come under severe category. So when you have a severe, this is basically air quality index directly affect the health a person. Okay, especially the people with old age and small children. So need to check the air quality index also. This is one of the reasons, basically, how we can get a clean air or good quality air. Further, you can see the contributor of this emissions, basically carbon dioxide emissions. I talk about around transportation. This is 14%. 14% of the air quality index is contributed from the transportation industry, 21%, and like that. If you see the worldwide, China is leading the chart, having being the largest emitter of the greenhouse gases. Second is US, then some food waste. India 6.4%, then Russia. So basically, yeah, we are in the category of the you can say the among the largest emitter of greenhouse gases. Now, this is a very interesting thing to know. We talk about basically low carbon grid, medium low carbon grid, medium high carbon, and high carbon grid. So what exactly the high carbon grid and low carbon grids are? So ultimately a grid which is totally, or you can say the energy which is injected into the grid, that is totally coming from the thermal power plant or coal-fired power plant, you can say simply, or you can say the energy generated from the coal that is coming from the coal. If the energy coming from the coal into the grid, that is termed as a high carbon grid. Or if you want to divide it, 93% of coal, let's say if in any grid 93% of the energy injected is coming from the coal-fired power plant, then we will say this is a high carbon grid, because ultimately you have won the coil in order to get the electricity. And with this percentage, if we move further for a low carbon grid, if you have a 0% coal and 97% zero emissions field, it means if the energy injected into the grid that is coming from the zero emission fields like solar, wind, or your water, that is called low carbon grid. Okay, in the same proportion, medium low, medium carbon, or medium high carbon grids are there. Ultimately, if you charge your electric vehicles from low carbon grid, then it makes sense in terms of environment, pollution, and all. Okay, so it is reasonable if you charge your electric vehicle from the solar, wind, hydro, or whatever. I mean, the energy should come from a zero emission fuel. In that case only it makes sense. Okay, so first thing is we need to learn what is high carbon grid, low carbon grid, medium low carbon, or medium carbon grid. Okay, so dependent upon the energy injected into the grid, from where this energy is coming, either we are firing coal or 0% coal, this is basically termed as a high carbon grid or low carbon grid. The all the content for now I'll be move further. See now, charging my electric vehicles, I
Hello, sir. Hello, sir.
you can mute your mic. So meantime you can note the questions. Yeah, please. Hello.
Sir, you are not audible properly, sir. I think.
So maybe some issue on your side actually.
Okay.
Here
Okay,
it
sir.
is fine.
Now it's audible.
Please check. Please check.
Okay.
Okay, no issue. So I'll request all of you that mute your mic. Just note down your questions. I'll keep around 15 to 20 minutes in the end for our question answer sessions. Okay. So it's okay now. Everything is fine. I'm audible. I'm audible.
Yes, sir.
Okay. So if I charge my electric vehicle from a grid, which is basically contributed from the coal-fired power plant, or you can say the grid where the energy is coming from the coal. If I charge my electric vehicle from that grid, you can see the level of emission. Here I have 11.7, 11.9, 12.2, 11.8, and then if I see the conventional engine, basically vehicles which is running on a crude oil or fossil fuel, you can see 13. So it won't have a much sense. I mean, you see the difference around 10 or around 12, and here 13. So yes, definitely there is a reduction in the emission, but not a considerable reduction in the emission level. Okay. Same time, if I charge my electric vehicle from a low carbon grid, already I have clarified what is low carbon grid. So you can see that in a low carbon grid, the emission level you can compare from a conventional vehicle which is running on a fossil fuel or crude oil, and the electric vehicle which is charged from the low carbon grid. So you can see the difference, basically what exactly the difference we have. Okay. Now further, so ultimately the conclusion is, if you charge your electric vehicle from a low carbon grid or simply from the renewable energy, or you can say the solar, wind or hydro biomass, then it makes a sense. Okay. Otherwise doesn't have a much sense in terms of pollution and all. So why electric vehicles? Already I have explained this thing. Now a lot of people have a growing interest in the plug-in hybrid electric vehicle, reduce fuel usage, greenhouse gas emissions, and you can say the world oil demand. Those two graphs are, I mean, enough to explain why we are moving towards electric vehicles. Okay. You can see the world oil production now since 1930 to 2050, the projection basically. So you can see that in 1970 the oil demand was less and the production was high. Okay, so cheaper comparatively. Then after that, 2010, both were matching, demand and supply were matching. But after that, you can see if the projection 2030 and then 2050. Okay, you see this is basically the gap between demand and supply. So now people are looking for a solution, that how to fill this gap. In order to fill this gap, people are looking for the options, and this electric vehicle is one of the options in that. Further, rise in temperature, basically, since we have a lot of pollutions and environmental due to environmental conditions, the global temperature is increasing. And if you see the global temperature increase, the ice of the glaciers will melt, and ultimately sea level will rise, and ultimately those issues are also will be there. Okay, so you can see the global air temperature since 1850, how this is rising. Okay, now what would be in 2010, what would be in 2020, just like that. Further, various emissions from the IC engines, carbon dioxide, carbon monoxide, then particulate matter, nitrogen oxide, a volatile organic compound. So all those reasons are contributed for an alternative. Why? I mean, we should go for some alternative so that we can at least have a sustained environment. So ultimately, all those are the reasons why we are going for electric vehicle. Now further, we have some advantage also comparative to that wide range of speed, health benefits. So health benefits already I have told. Less vibration while driving, I mean silent, cheaper to maintain in comparison to IC engine vehicles. So apart from using this electric, we have other advantage also. That ancillary services, that I'll come to know. I mean later on when I'll go in a lab section, then I'll explain what exactly the other advantage we have. Right now, we are just concentrating over the environmental point of view, that we are going for electric vehicles, and some global issues are also there. That's why we are going for electric vehicles. Now, what are the other advantages for the electric vehicle? That also we will explain. So, the classification we can do that: internal combustion engine, hybrid electric vehicles, battery electric vehicles. Then further, comparison of electric vehicle and this internal combustion engine basically. So you can see that this is the internal combustion base vehicle, the emission level, and you can see the electric vehicle emission level. You can see there is a world of differences among the between this emission if you compare this IC engine base and electric vehicle basically. So this thing already I have told when I talk about that. If you, this is basically when you charge your electric vehicle from the low carbon grid, and this is the efficiency comparison in electric vehicle: 100% electricity, then battery, then motor drive, and ultimately wheels. But if you go for a internal combustion vehicle, we have a petrol, then up to engine, this is only 20% efficiency, then 70%, ultimately left with a 16% efficiency. This is basically analysis, comparison, basically how the electric vehicle is superior. Then further, this is basically well to wheel. Well means we are extracting the oil from the well, and once it is coming to your vehicle, this is basically the well to wheel analysis for a electric vehicle and internal combustion based vehicle. So you can see crude oil, then refinery, it went to refinery, then after that power generation, transmission, then battery charging, then ultimately you are getting 18%. And here you can see the only 13%. So if you compare in that sense also, further electric vehicle is better than the internal combustion based vehicle. And if you, now we'll come to the challenges basically. So till now we just came to know that what exactly the electric vehicles are and why we are using electric vehicles, why the electric vehicles are important for our country. I mean, and maybe this is in terms of maybe in terms of environment, maybe in terms of cheaper or other issues. Okay. So what are the importance of those electric vehicles that already we have covered? Now the next one is, what are the challenges? So if we talk about the challenges, I have summarized all the challenges in one slide. So yeah, this one is basically what are the challenges. See, if everything is so fine, so glossy, so lucrative, then why we are not having electric vehicles all the way? I mean, why now all should have electric vehicles? Okay. So, but we have a certain challenges basically. Those challenges are predominantly technical challenges, infrastructure-wise challenges, policy and market. So if we talk further, under technical challenges, we have efficiencies of batteries, a driving range of electric vehicles, charging time, safety and environmental impact. Now, battery is a critical component in a vehicle, electric vehicle. So we have a certain technical issues regarding batteries. One is efficiency of the battery and their driving range. My student in the lab, they are working on electric cycles and electric vehicles or electric bike. Also, after 5 or 6 months, we will start on electric car also. I mean, ultimately we will convert. Even I'm trying to convert my car to the electric. So let's come to the point. In electric cycles we have developed, and I'm using those electric cycles in the campus itself. So battery is around 10 ampere hour battery. So right now outside of my office, it is in the charging mode. So generally it took around 2 hours to get completely charged. And in a single charge, it roam around 35 kilometers. So if I'm traveling in campus, coming from my home to office and going back or moving in campus itself, 35 kilometers is fine. And after, generally I charge it again after 7 or 10 days. This is fine with me, no issue. But for example, I have to go from Jaipur to Delhi. This is around 300 kilometers. So do I have any battery which can charge faster? First thing, then can have a driving range of 300 kilometers so that I can safely travel to Delhi in a single go. Let's say if it discharge in between, I don't have a time to wait for 2 to 3 hours in order to get it charged. Okay. So ultimately the reliability. So my battery should be in such a manner, it should be efficient. It should have a high driving range. Charging time, it should have a less charging time. See, if I go to refilling station or fuel station, it hardly took 5 minutes or more, less than that, even if we don't have a queue, less than 5 minutes. Okay, and we get it our tank full. But is it possible same in case of electric vehicle also? Right now the charging time is too high, even 2 to 3 hours, 3 hours also. So let's say I'm going to Delhi and in between there is a drainage or my battery is, I mean, drained out. I don't have time to sit for 3 hours, then get it charged and again start like that. Okay. So these are the predominant issue right now in electric vehicle battery charging or charging point of view or battery point of view. So a lot of people are working in this area. Even they have developed few batteries. They are, I mean, lot of material science people are working in this area to get the good battery material so that at least we can have the reliability we are enjoying in right now in a internal combustion based vehicles. Okay. So the efficiencies of battery, driving range of the battery, charging time, those are the critical issues basically. So depending the user centric or depending upon the use, I give one example of my cycle, electric cycle. I'm fine with this because my travel route is, I mean, narrow or small travel route I'm following. I don't have any issue if it get 2 hours of charging right now because I'm sitting in my office and I mean I have a time it can get charged. But depending upon the usability and depending upon the requirement, depending upon the need, it can't be a universal. But yes, if I have any battery which can quickly charge or having a driving range high, my problem will get sorted out while traveling to Delhi. So this is a one big technical issue right now we have in terms of batteries. Environmental impact after completely drained out, or let's say uh, when your battery is not in use, so scrap you can say material. So do we have a proper mechanism in order to, I mean, to say manage waste management for this degradable materials like that? Okay, so these are the technical issues related to battery. Now come to the infrastructure point of view. One is charging infrastructure, smart grid, battery recycling, dedicated lanes for electric vehicles. Charging infrastructures, let's say I own a vehicle or I have a cycle. My cycle, I can simply charge it through a 230 volt and 5 ampere switch also. Okay, not an issue, AC charging right now. But if I have electric vehicles and moving on a highway, do I have a charging station on the highway also, or do I have a charging station spread throughout the city? That is the comes under charging infrastructure. Do we have that? If I own an electric car in the from the market, do I have those facilities right now? That I need to think first, because I know that fuel stations, refilling stations are everywhere. If I go from Jaipur to Delhi, I will find around 100 of refueling stations both side. Okay, but not a single charging station right now. So this is basically infrastructure wise challenge, that we don't have a infrastructure right now. But yes, government is working on that side. Even I heard Nitin Gadkari, he's basically very responsible person and managing his ministry nicely. So I mean, in a coming future, definitely we'll see a lot of charging stations and all would be there. Now, smart grid. Ultimately, you are charging your vehicles. Let's say in my campus, I have 1,000 of electric vehicles. Since we have a population of around 7 to 8,000, including student and faculty in a campus. So I have, let's say, out of it, I have 1,000 electric vehicles. One average electric vehicle battery is around 10 kilowatt hour average, medium segment. If you go for a higher segment, the size of the battery will increase. So 1 kilowatt hour roughly give you 6.6 miles. Okay. So in a from a 10 kilowatt hour battery, you can go around 80 to 100 kilometers, something like that. Average, roughly, I'm giving this approximate figure. Okay. So let's say in a campus, people are coming 9 in the morning and keeping their vehicles in a parking lot, and they are leaving at a 5 o'clock. Okay. So 10 kilowatt into 10 kilowatt hour into 1,000, this is around 10,000 kilowatt hour or 10 megawatt, you can say. Okay, 10 megawatt energy right now available in the parking lot. And you can say that almost all the electric vehicles are 80% SOC, having 80% of SLC. So roughly 8 megawatt of uh, 8 megawatt of power is available right now in the parking lot, and it could be treated as spinning reserve. Okay, 8 megawatt of power in terms of battery energy storage, this is available in the parking lot, and it is just like a spinning reserve basically. Okay, it is your spinning reserve. So now, is it possible if you can divert this available energy in some of area of the city where there is a frequency drop, or maybe a you can say emergency load is there? Okay, can you divert this? This is one thing. Second thing is, when in my campus, let's say 1,000 vehicle, but in a whole city where we have a population of around 50 lakh, let's say 1 lakh or 2 lakh or 5 lakh electric vehicles are there. They generally charge them in the night mode, since in the daytime they are busy or something. So we can expect that around 70 to 80% people charging their electric vehicles in the night time. So when at a time you are plug in the vehicles into the grid, so whether our grid are capable of handling such type of load. Okay, these are also under intermittent load. They're kind of intermittent load, just like a wind and solar. So ultimately, we need a smart grid which can capable of transferring spinning regime into area where there is a frequency drop. One thing. Second thing is, at a time when all vehicles are plugged in, our grid should able to maintain the proper decorum. Okay, so that's why we need a smart grid, just to hold or just to handle the intermittent nature of the electric vehicles. So do we have a smart grid right now in infrastructure? That we need to think. Then battery recycling. Basically, there is one component or one topic, battery swapping. Means, for example, there are battery swapping stations. Let's say I have electric vehicles. So I'll keep two batteries. One will be in the discharging mode and one will kept idle. Okay. Let's say one of my battery got drained out. I can switch idle mode battery into the discharging mode and can take out the used battery. Okay, outside. And I can go to the swapping station that this is my battery which is fully drained out. Now you take it and give me a fully charged battery so that I can keep again as in a idle mode, or you can say as a reverse reserve. Okay, so those are called basically battery swapping stations. So those battery swapping stations will enhance the reliability of the overall system. So ultimately, if you want to have a charging station, at least have a battery swapping stations, so that I need not to wait for a longer time. Just swap my battery, have a two battery at a time, just like a stepney. You got puncture, you remove the one tire and another tire you can put in, so that the work can still go on, just like that. Okay. So similarly, we could have a battery recycling, or you can say, yeah, battery recycling or the battery swapping stations. Recycling can be done at a faster pace. Okay. Now another point is dedicated lanes. So we can think of just like a VRT corridors or other type of dedicated corridors for buses. Simply we can have those dedicated highways or dedicated roads for the electric vehicles also. Now, after those technical and infrastructure challenges, we have a policy: taxation of vehicle and component, subsidies on fossil fuel, electricity tariff and policies. So basically, we can reduce the tax on the electric vehicle, because electric vehicles are so costly right now. Okay, so we can think of reducing the tax on electric vehicle as well as its component. Just like we are giving subsidies on fossil fuel, so we should think of, or simply in a single word, we should have a policies to enhance to enhance the ownership of the electric vehicle, so that people can attract toward the ownership of the electric vehicles. We must have our policy in such a manner. For example, we can say that the people who are owning the electric vehicle, they need not to pay toll tax, for example. So dedicated lane we can create for them. That if you have an electric vehicle, just like right now, if you have those um, what we say that if you're passing through a toll tax, then we have that card, smart card. So uh, it will automatically deduct your money. Then simply, if you have an electric vehicle, you go for that line and you need not to pay any tax or any toll tax. So there's those kind of basically the policies could be there. So people can adopt, lot of people can adopt electric vehicle. Even in California, they have a charging station. They have a policy. They are giving a huge subsidy so that people can adopt a lots and lots electric vehicles, and they are doing that. Even at a UCLA campus in 2014, December 2014, they were around 212 charging point. Now this is a 6 year back I'm talking about. Definitely they have increased more now. Even their student, their faculty member, they have their own electric vehicles. Now, after this challenge, we are coming to market side challenges basically. One is testing and certification, vehicle servicing. So, if you say testing and certification, for example, we developed this electric vehicle, electric cycle. So the range of the cycle is 25 kilometer per hour. So this is the range in which you need not to have any certificate from the RTO, like no registration, no helmet. Even you need not to follow the traffic rules also. If you can, with your cycle, you can cross the red light also, like that. Okay. So ultimately, you can wear helmet for your safety, but it is not mandatory as per the rules. Okay. But once you move above this speed, for example, for electric bike, you need to go for everything, testing as well as the certification and all from the particular institute. So, do we have a proper institutions for certification and testing? Right now, Pune, I think ARI Pune is there. I hope you have included few speakers from those also, from there also. Those people are doing that. So ultimately, the thing is just like the IC engine based or vehicles, we have so many things because that is established market. Okay, we have a servicing also. For example, you are purchasing any car for Tata or maybe Hyundai or maybe Maruti. So you know that those are the service stations there. So you don't have any issue if there is some fault in your car. You can simply go to service station and get it done, get it checked and get it done. But there should be same availability for electric vehicles also, but right now we don't have that. Okay. High capital cost and financing. So I hope this is there, that if you are purchasing an electric vehicle, the finance should be available. A raw material for batteries, this is also big issue that I'll discuss in my further next slide. So these are the basically some challenges basically in order to develop the electric vehicle market as well as their design development and all. Because okay, everything is ready with you, but if you don't have a battery, proper battery or good quality of battery, then what you will do? Okay. So simply these are the one slide in which we can think of all the challenges available in order to get hindrance for a electric vehicle adaptability, ultimately we will say further. So these are the already I have discussed. Now I'll come to basically electric vehicle charging infrastructure, because since I have to talk about the design and development of charging infrastructure. So till now we talk about why we need electric vehicles, first point. Then second point is what are the challenges in adopting electric vehicles. Now we'll talk about electric vehicle charging infrastructure and several components basically. So I'll discuss about battery also separately. I'll discuss about battery also in detail. So for the charging point of view, the global electric vehicle charging infrastructure market size is expected to reach around 72.5 billion by 2025. And ultimately, you can see that a lot of companies, power electronics based companies, they are working in this direction. Even in my campus at MNIT Jaipur, we have around 4 charging stations, but unfortunately nobody is using, since no one in the campus is having electric vehicle. And those chargers installed by the REEL, there is the Rajasthan Electronics and Instrumentation Limited. We have a lot of alumni of MNIT in those REEL, basically, starting from MD to general manager and all other people. So they are always too kind for MNIT, and they installed 4 chargers, but unfortunately nobody is using. Since we start developing some bike and cycles, not cars right now. Well, within a 1 year we will develop electric car also. But right now we are only working for those e-cycles and e-bikes. And for those we need not to go for those charging stations. We can simply the charger which we have developed for those e-cycles and EVAC, that is simple a charger which can plug into 230 volt and convert that into DC and simply charging that 10 ampere battery and bigger battery. So now, since the growing sales of electric vehicles are anticipated to drive the global market, and people are thinking, since a lot of e-rickshaws are there, a lot of people have buy electric scooters, car also. So now even industries are also thinking in that direction to develop those charging stations. So this is basically, as I've told you, that global electric vehicle charging infrastructure, this market size is reduced, I mean, increasing by like anything. So further, this is a basically electric vehicle market size and forecast for India, that how it will go further. The growth rate is around 20% from 2018 to 2025. So a day will come when a lot of people will have electric vehicles, and this is a common practice in India. You will find a lot of charging station and everything, and even service stations also. Whatever challenges I have told in the last slide, so those basically met out, and I think we will have a lot of electric vehicles on road. And I'll give you one example, that when solar started, the cost of per unit energy generated from the solar was around 27 rupees. Now you see this is below 2 rupees right now. So this is something how the change comes up with the advancement in science and technology, with the advancement in power electronics, the conversion techniques, MPP techniques, your converter, inverter, it drastically reduced from 20, more than 20 rupees to less than 2 rupees right now. So similarly, the things will happen in electric vehicle also. So this is already I have told. Now we'll come to the real stuff basically. So this is basically a diagram, a common diagram for an electric vehicle, generalized, not more technical, but yes. We have a grid. So we have basically two type of charger, onboard and offboard. On the name itself self-explanatory. On board, everything on the vehicle. Off board, outside of the vehicle, and you are simply using the switch to charge. So when this is on board, so your everything, battery, your charger in the onboards, and simply a plug you are taking out and you are charging this. So on board. Off board, your accessory outside, battery is inside in the vehicle, and you are charging this. So this is a four-wheeler. Basically, we have this AC to DC converter, then DC to DC converter, and ultimately, with the help of this DC-DC converter, we are charging this battery pack. Energy stored in the battery. Now, with the help of this battery, by using one inverter, convert this DC to AC and running the electric motors. Basically, which type of motor you are using, that depends. Okay, for a low speed or something, I mean, in a low power rating, here in our cycle we are using a hum motor, that is basically PMLDC motor. Okay, so if you are using some induction type motor or other motor, so definitely you need this. So convert this DC to AC, and now you are running this motor, and some part of this battery energy you are using for a auxiliary supply, your maybe wiper, or maybe your small supply basically, for that you are using. So people who are doing their MTech or PhD, they can think about, I mean, especially for power trust people, they can think of this one stage AC to DC conversion, can develop different type of topology to convert this AC into DC. This is one area of research people can think of. Second is DC-DC converter. So here in DC-DC converter, basically people can think of developing DC-DC converter topologies in order to charge this battery. Then third one is battery energy management or smart charging algorithm can be developed in order to charge this battery. Okay, and after that drives. Basically here one can talk about different drive or can develop some drive also. For example, right now whatever we are using, those hub motors in our cycle and bike, that are imported from China, and unfortunately whatever uh, made in India, that is not up to the mark. A lot of issues are there in that. So simply people are buying from China and assembling in India. So one can think of developing their own drive, that indigenous drive. That is one target first people can take off. Why I'm saying this? In 2018, I was in a meeting with I was in meeting at IIT Guwahati with those Ashok Leyland and Hero Electric and Tata. All those people were there. I simply asked one question that I'm working in this electric vehicle area, so I need a real-time feedback from the industry. What exactly the problem you are facing, so that jointly we can develop something. Then the CTO of Ashok Leyland simply told that we are not doing any R&D. We are simply purchasing from China and assembling it. So since we are talking for Atmanirbhar Bharat and indigenous things, now we should accept the challenge of developing our own drive for those cycles and motor purpose. So this challenge one can take. Even we are also trying. We have even submitted one grant in order to develop this motor to one of segment of DST. So we are thinking of that. So this is the overall picture of the, see, whenever we are talking about the electric vehicle, we are talking for this electric system. So this is the overall picture for an electric system in an electric vehicle, what exactly the things are and how to design that. Okay. So designing of this DC-DC converter, DC AC-DC converter, DC-DC converter design for this battery, and these are the major component for that. Ultimately moving further, so these are your level 1 charger, level 2 charger and level 3 charger. Till now in our laboratory we have developed a level 1 charger that is around 230 volt and 1 kilowatt range. So we have a AC charging, we have a DC charging. So DC charging, the range are given for level 1 200 to 440 volt up to 20 kilowatt, and below level 2 200 to 440 volt, and this is a 20 to 80 kilowatt, and if more than 80 kilowatt, this is in a level 3. Similarly, we have a AC charging of level 1, level 2 and level 3. So level 3 is basically for either single or a 3 phase. So below 2 kilowatt it will come under level 1. Below, I mean above 2 kilowatt and up to, or you can say up to 20 kilowatt, that will come under level 2. So this is basically AC charging and DC charging. Further, this is an old picture of a charging station. Now you can say that we have a charging, we have a parking lot, and on the rooftop of the parking lot we kept some solar, something like that. So this is how electric vehicle work, that already I have told with the help of this diagram. This is the diagram basically. The help of this I have already told. So whatever we have written there, that is basically the same slides. Now we have some protocols basically. See, if you talk for a complete electric vehicle, this is a combination of electric, mechanical, computer science, electronics people basically, and even architecture people also. So there are some charging protocols. There are EVSC, that is electric vehicle service equipment. So Sedamo charger is basically developed by Japan, and this is basically J1172 trademark of basically a company. So AC charging, level 1 AC on-board charging, level 2 AC on-board charging, and level 2 DC off-board charging. So the Sedamo is basically off-board charger developed by the Japanese companies. So this is basically some protocols how to charge they are they are the basically communication protocols for charging. So this is a separate task for communication people. But yes, as I told you earlier, that is a combination of electronics, electrical, say, computer science, mechanical, and even architecture people. So off-board, on-board, already I have described what are the on-board charger and off-board charger. I'll share those slides later on. Now, basically, slow, because I talk about the slow charger and fast charger also. So electric vehicle charging infrastructure, those are slow charger or fast charger. Sedamo, already I told you, electric vehicle charging infrastructure, combined charging system. Then we can have a commercial also and residential also. Let's say you own an electric vehicle, the same electric vehicle you can keep in your basement of your building, and that would be known as a residential charging point, or commercial, that is available maybe at a roadside or highway side, or maybe in a parking site if you go for some municipality or somewhere. So they have a public parking, so that could be in the commercial category basically. So now further, what is basically the electric vehicle charging ecosystem? So you can see that a charging lot is there. You have your vehicle park, just like I gave an example of having a 1,000 electric vehicle park in a charging or in a basically parking lot. So those are basically how the ecosystem works basically. You have a 1,000 vehicle park in a parking lot. So you may be charging it through solar or something, but same time, as I've told you earlier, that let's say 8 to a megawatt of energy is lying idle. If there's a frequency drop in some area, can you transfer that 8 megawatt, or maybe out of 8 megawatt, 4 megawatt or 5 megawatt to that area? How you will do that? So basically, remote user monitoring and grid monitoring. Same time you are monitoring the grid, then see that if there is a frequency drop in that area, can you give the command? Can you give the command so that you can send those extra energy, or you can say the 5 megawatt into that area? So this is basically how the system works. Energy generation, that is another part. Okay, grid monitoring and remote user monitoring, this is the main part. And management of fleet. Management of fleet is basically, you have a parking lot, 1,000 vehicles are there. You don't know when a vehicle will come or when it will go. Okay, so maybe one person is coming at 9 a.m., another maybe 9:15, 9:20, maybe one is leaving at 3, one is leaving at 2 p.m., like that. So this is a management of the fleet. So ultimately, there's a full-fledged automatized charging ecosystem would be of this type. So vehicle to grid and grid to vehicle, V2G and G2B, both can be managed with this type of things. So as already I've told, that combination of electric, electronics, computer science, mechanical, all streams are here. Now further, I'll give an example from the UCLA basically here. They have a one mobile app regarding electric vehicle. They have a basically their fluctuating tariff plans. Okay, unlike our country, they have a flexible tariff plan. Like depending on the demand, their prices will increase or decrease, like that. So having a mobile app, that they will come to know what are the electricity price right now. And since you can keep your electric vehicle in the charging mode with your mobile app, that you can fix that when the electricity charges are up by this amount or up by this amount per unit, my vehicle can come into discharging mode. Okay, or if the electricity price are less than this I mean less than this amount per unit, my vehicle can go into the charging mode. So you can manage. just like some people do in stock market. Okay, so ultimately one can do this. So this is vehicle to grid. See, once you see that electricity prices are high, you can monitor and you can ask your vehicle to discharge into the grid. And when electricity prices are low, you can ask your vehicle to get into the charging mode. Similarly, can be done in a parking lot with a fleet management, that when there is electricity requirement in the area, these vehicles can go into the charging mode, and these vehicles can come to the discharging mode, like that. Okay. So further, these are the power resource converter that perform the necessary functions for charging a battery. These are the particular base, cable, connector, and stations. Then electrical supply equipment. So this is basically prevent EVAC, a protocol basically to keep user and electric car safe while charging. Using two-way communication between the charger and car, the correct charging current is set based on the maximum current the charger can provide, as well as the maximum current car can handle. Okay, so that's why we need an electric vehicle supply equipment. So the ultimate purpose is preventing current from flowing when the charger is not connected to car. It ensures that if cable is not correctly inserted, power will not flow. EVAC can also detect hardware fault, disconnecting the power and preventing battery damage, electric shorts, and etc. So this is basically the global deployment target of deploying the charging infrastructure as per this Equator Protocol or Paris Declaration on environment, that over 100 times increase in the EV charging infrastructure all over the globe in next 15 years. Basically, this Paris Declaration was basically conducted by keeping in mind the environmental issue and all. So it was declared that in the next 15 years, 100 times more charging infrastructure will be developed. And what exactly the 2020 then 2030, just like that. So if you go, I mean, already I have explained onboard and off-board chargers. So now you can also understand right now with this example. Onboard charger is basically inside the electric vehicle. This is the only difference you can see. Okay. On board, the name itself suggests boarding. Charger is boarding in the vehicle itself. And here you have a charger outside. Just a plug, with the help of plug, you are doing that. Okay. So that is basically the difference is low power rating and high power rating. So the onboard is basically low power and slow charger. Simply just like in my cycle, which is kept outside for a charging. So I am just taking a plug and plugging into the 230 volt 5 ampere and started. So since everything is inside that box we have created. But if you have and this cycle is only having a 10 ampere hour battery. Ultimately, I'm saying low power battery. Okay, and so this is a slow charger. But if you have an off-board charger, that is basically for high power and fast charger. Further, this is a basically electric vehicle recharging system. Now you have a grid. You already I have explained this AC to DC. Then with the help of DC, you are charging the battery. AC-DC converter is used to rectify the AC voltage and ultimately converting into the DC. DC-DC converter is used to adapt the rectified voltage and a level compatible with the batteries. Let's say battery need a 24 volt. So DC-DC converter will do that. Then further, so we have a type of charging, conductive charging, that is called AC charging or DC charging, and another is wireless charging. So in wireless charging, we have a transmitter and one receiver. I'll explain about it. So in conductive charging, basically we use a cable. Okay, just like cycle which is getting charged outside. But in a wireless, we don't need to have that cabling. There is a gap between transmitter and receiver, just like the transmitter will be in the road, and with the ground clearance or in a vehicle itself, your receiver is fixed. So from those transmitter and receiver, the charge is transferred wirelessly through conducting medium, and ultimately there is a charging of the vehicles, electric vehicles. So all those DC charging, AC charging is explained. So this is a graphical comparison between all the possible charging levels. This is some data basically. Now further, if we move mode of charging, this is a 250 volt single phase or 440 volt three phase with a maximum current of 16 ampere. Doesn't have extra control pin for production. This is a mode 2 charging. This is 250 volt single phase and 480 volt three phase with maximum current of 32 ampere. Mode 3 charging, maximum current of 250 ampere. Then mode 4 charging, 600 volt DC including earth and control pilot, maximum current of around 400 ampere. This is expensive. Now wireless charging. So in wireless charging, you have one transmitter and one is receiver coil. So you can see that there is a ground clearance between the vehicles. So I think in our lab we are able to propagate, or we are able to transmit with a around 270 mm or 27 centimeter gap within a transmitter coil and receiver coil. So that also hardware part I'll discuss in my earlier next slides. So this is basically inductive charging or wireless charging. It generally transferred. So vehicle to grid to vehicle already I have explained that we can vehicle to grid, we can transfer the energy in a area where there is a frequency drop or something like that. And this is also a kind of wireless charging, that track coil 1, 2, 3 like that. So your vehicle is moving, and while moving also it can get charged. Or can think of this type of thing also. Let's say we have electric bus. Electric bus is stopping at every 2 kilometers in a city. So at every 2 kilometers you have a charger, wireless charger fixed in a road. So whenever there's a bus coming, stopping for 2 to 3 minutes, again get recharged. Next station again get recharged. Like that also can be think of. Static charging or dynamic charging. Basically in a wireless, one is that you stopped your vehicle on road and it getting charging from wireless, just like first picture, static charging. You park, charge and go. But you have to stay there. Okay. Second one is dynamic charging. You are moving and charge on the go. See, the difference is park, charge, go and charge on the go. So you are moving and same time you are getting charging also. Hybrid. In hybrid recharging, you have a solar as well as a grid. So both way you are charging your battery. Here ultimately your battery is there. So these are basically type of connector. If you have a simple low power charger, so this 3-pin pointer is fine. Even 2-point plug is fine. But if you move further, depending upon the protocols and all, you have this type of connectors. So basically, we have just a 2-pin plug, no, 3-pin plug. Sorry, 3-pin plug only. Okay, that is less than 2 kilowatt you can use. But if you move further, you have another type of Sedamo chargers, CCS, Tesla, so many others. So their chargers are different. I mean, their connectors are different. So every vehicle need to have a onboard charger. So these are the basically I earlier discussed SAE J1172. So these are the basically 5-pin connector mainly used for North America and Japan. And this is a Sedamo, IC62196. IC 62196 7-pin connector, mainly used in Europe. So these are the combined charging systems basically. That this charger developed by Tesla. This is somehow we are using right now. In a few cars, you will find this basically, this type of charger, which is India using right now. So this is a charging station, electrical charging station will look like this way. These are the few charging stations. Now, one important part is batteries for electric vehicles. Basically, in electric vehicles, we are using lead acid batteries, nickel, cadmium, nickel metal halide, or lithium ion batteries. Most of the e-rickshaw user, they are using lead acid battery basically. Okay, if you have ride this e-rickshaw, you might have asked somebody or may have inquired. Basically, in e-rickshaws, a typical battery size is around 48. Rating is around 48 volt, 100 ampere hour. So around 5 kilowatt hour something. So they roughly move around 80 kilometer in a whole day. Just came back to their home and plug in into charging mode. All night it will be into charging mode, and ultimately morning they are again ready for the same. Okay. But whatever available with this right now, you can see in this range, lead acid battery around range is this, basically specific energy, nickel cadmium, nickel metal halide, and lithium ion. So lithium ion is right now having around this one, 160 kilometer. Okay. And further, future lithium ion or zinc, those are under development basically, and future R&D is basically lithium air. So from this slide, you can find out that ultimately you need a lithium everywhere. You need a lithium in all type of batteries, almost. Okay. Whether this is a lithium ion, future lithium, lithium sulfur, or lithium air. Do we have enough lithium right now? This is also concern in the challenges. My earlier slide, when I was talking about the challenges, I have one point, raw material for batteries. So now I'm discussing this basically. You can see from here that lithium is a very, very important material for batteries. But if we see the lithium producing countries, Australia, Chile, China, Argentina, Zimbabwe, Portugal, and Brazil. So we don't have those reserves. We have to depend upon another country basically for those reserves. Now, when we have to depend on another country, we need to see our foreign relation and so many things. And I mean, trade possibilities and what we can give them in back. So many issues are there ultimately. So, but the truth is that we won't have that much of availability of the lithium right now. Okay. So need to think about it. These are the few lithium producing companies, sorry, not lithium, the battery producing companies which are developing or manufacturing the batteries. Now I'll come to my lab basically. This is a lab which we have developed at MNIT Jaipur when I joined. So this is a smart energy and sustainable research lab. These are the few funded projects we have. One funded project we have finished in this July, that is basically development of electric vehicle chargers. That was a grant given by DST. So we have developed some unidirectional, bidirectional as well as wireless chargers in this grant. We filed one patent as well as we have published in IEEE transactions and IT Power Trust from that projects. So this is one project. Second project is around 3 crore grant we got from DST. That is basically we are developing a microgrid in a village near to MNIT Jaipur, around 16 kilometers from MNIT Jaipur. The beauty of this microgrid is basically this is completely isolated, as well as we can, if we later on we want, we can send into grid mode also. But when this is isolated mode, the reference generation we are developing through battery only. We are not using any reference generation. Generally, in all the microgrid, they have a reference generation either from grid or maybe diesel generator or whatever. But here the reference is basically from the battery itself. So this is the only beauty of this grid, and this is unique work, I would say worldwide, since we have a four universities: University of New South Wales, UCLA, USA, ETS Canada, and UIT Norway. Those are collaborating with us in this project. So due to COVID, we got delayed, and now we got extension of around till July 2021. So we are looking forward to complete this project. We are on the verge of installation only right now. Everything is completed. So once this is ready, we would like to invite all of you to visit that microgrid site. It's a real-time work, which is basically benefiting the village people. So right now this is only microgrid, but further we are also thinking that can we relate this microgrid with the employability and the income of the village people. So that would be the next stage when we got more funding from some other source. After this, we have another project that is basically Spark. Basically, this is a joint collaboration between the University of New South Wales and University of Concordia. This is a cooperative microgrid integrated smart electric transportation. So basically, this grant is exchange grant type thing. Foreign professor can visit our lab, stay here for a month or more, can guide our student, can teach some course. My student can visit their labs for a 3 month each, and their student can also travel to India and can work with our team here in MNIT. But due to COVID, only one professor can visit till now. Rest of the things are as it is. So we are hoping that it would end and soon our student or their student can visit, and mutually this project can be completed. So till now only Australian professor has visited us around 21 days, and they work with us together like that. So these are the few projects working right now going on in lab, and one more project is also coming. I hope to get sanction order soon. So basically, since we are talking for electric vehicles, so I'll discuss only our one project in which we are developing electric vehicle chargers. So only that I will discuss in detail right now. So we are developing unidirectional, bidirectional, and wireless chargers. In wireless, we have achieved the distance of 270 mm. So basically, while developing charger, what exactly we are talking about? See, that we are going to make a charger that already I have told you that we have developed only level 1 chargers till now. That is up to 1 kilowatt only. So whatever we have developed, I'm using for my cycle charger, and those only we have developed. So when we are talking to develop a charger, basically we think what we can do to develop a charger. So ultimately, if you can reduce the size of charger, can increase the efficiency, can decrease their losses, or ultimately, I would say in summarize that size, cost, weight, efficiency. So these are the few things you can work on the charger side. Okay. So when I have told you cost, size, weight, efficiency. So these are the point on one can work. So we targeted those things and we try to work on that. So in order to reduce the size, cost, weight, and then increasing efficiency, what we did, we just follow the simple principle of power electronics. Now, here I have already told that we have developed the last charger. Okay. So basically, DC-DC converters are predominant in case of a charger. So high power density, high efficiency, high reliability, and economics. All those things comes under this. So now which switch we select, either MOSFET or because your charger that would be maybe IGBT based or MOSFET based. Okay. So ultimately, if you have a high frequency, a low power rating, then MOSFET. If you have a low frequency and high power rating, then IGBT. Further, as I've told you that for a charger point of view, see this. How to reduce the losses. ultimately there is a one term soft switching. The people who are with power electros background, they must aware about the soft switching. Or if not, then you must be aware of at least this this characteristic, voltage current characteristic of a device. So this is simple, that if you operate your switch in cutoff region or this linear region, okay, your if you are let's say you are operating a cutoff region. If you are operating cutoff region, ideally your current is zero. I would say ideally, okay. In this region, in cutoff region, ideally your current is zero. So P equals to V into I. When your current is zero, you have a power zero. And if you are operating in this linear region, ideally your voltage is zero. So P equals to Vi, again power is zero, ideally. Okay. So ultimately here I am saying zero current switching in cutoff region and zero voltage switching in linear region. So in power electronics, we have to operate our switch either in cutoff or this linear region, so that ideally we can have a power loss zero. People have used this. This is called basically soft switching, a soft current switching or soft voltage switching, like that. But in a charger, when you start from light load to full load, you are able to achieve soft switching very nicely. But at light load condition, the soft switching got lost. So by adopting some modified techniques of PWM, by changing the configuration of the switches, and by other means topological change, by PWM change, or by selection of the switch also, we are able to achieve this soft switching on all range, complete range, starting from low load to full load. Okay, this is something we have achieved, and based on that we have published. And ultimately you can see that if you are not operating in a either cutoff region or linear region, then if you are operating in this region, so you have a voltage and current, and losses will be very high. Okay, so what we did in roots loss the losses, we operate in cutoff region or in linear region, so ultimately achieve soft switching, and soft switching in all the region, all the load, that is something we achieved. So these are the few results we got. And even in switch also, let's say MOSFET, we have a three type of MOSFET in the same range: IRP 460, IRP, IXFN 64, N60P, IPP 65. So now which one you have to select? So we went to the data sheet, and based on data sheet, we found that the value of resistance is less, and ultimately the total losses are less. So you can see that in with a different MOSFET, different MOSFET, we have a different efficiency. Here we got 94%, here we got 95, 96%. If we see the cost, the cost of this one is 1800, here the 800, here is 300. So we choose that 800. Although there is a trade-off between cost and the efficiency, but we choose this 800 rupees since we are getting highest efficiency in this. So this is also one criteria how to select the switch and how to use it so that you get a maximum efficiency in that. So based on this, we developed those chargers. These are the chargers that we have developed in our lab. And I would like to tell you that everything, I mean, from the scratch, everything is developed in lab only. Even we didn't go out to fabricate our PC. We fabricate our PC also in the lab itself. Also, I mean, although we use a traditional method, but we have developed everything here only. But sometime when we got comment in the paper that use some professional things like that, then we contacted in Ahmedabad and Bangalore, and we got fabricated for our another project some PCB from the Bangalore itself. Okay, so these are the chargers we have developed in lab. This is, you can see the soft switching we have achieved. Here you can see the voltage is zero. I'm not going more technicality, basically just to introduce basically what we exactly we are doing. And these are the comparison of the losses with the modified PWM techniques. I told you that in order to reduce the losses, we use modified techniques of PWM. We change the configuration of the circuit, and ultimately we are able to reduce the losses. So you can see this is the comparison of the other people which worked in the area. And ultimately, these are the few other topologies we have developed. So you can see the comparison basically. With the PWM, we are getting around 6% more efficiency. 6% more efficiency we got. This is the efficiency. And ultimately, this is basically a charger which is given to us from a company came to us. They gave this charger to us, and they again want to the weight of this charger was 3 kg, and they want to reduce it 1 kg, and efficiency was around 70%, and they want to increase it. So ultimately, we reduce the size to 1 kg and increase the efficiency from 70 to around 90 to 93%. So this how we achieve this, simply already I have told you that these are the techniques we used and we have achieved this. So second one is bidirectional power flow. Means we charge the vehicle from the grid and then we discharge it. Basically, this is a DC to DC bidirectional power flow, not from DC to grid. All means we have not taken vehicle to grid. This is just a bidirectional. We charge and discharge the battery, but by discharging we didn't send to the grid. So this is basically a DC-DC converter, which we developed in lab for the bidirectional point of view. This is work of MTech student who developed one universal charger which can go into charging mode, proportional mode, regenerative mode also. This is a MTech student right now working in Northeast somewhere. So ultimately, wireless topology, we have a charger. The wireless charger I talked about earlier. This is a transmitter call. This is a receiving call. The distance between this transmitter receiver call is around 27 centimeter, and this is ultimately a charger circuit, total charger circuit. This is a battery here, this side. This student submitted his thesis. We are waiting for his defense. So ultimately, last in the end, our student, my BTech and PhD student, they have incubated this startup in MNIT itself, since the government of India gave mandate for MNIT and IIT people that student can incubate their companies. So my student have incubated one startup. So they are indulging in developing those electric cycles and electric bikes right now. I'm a mentor for those students basically. So they have developed this cycle and claiming that 35 kilometer in just 3 rupees, or around 60 kilometer in 3 rupees, like that. So this is developed by a student. These are the few other segment. I mean, when they started they have some different type of model. This is a battery, if you can see here, but now in the next model, the battery is shifted to some other way. So this look more nice. This is developed by our student only. Everything is starting from welding to everything is done by the student only. So these are basically cycle come bike, but the speed is 25 less than 25 kilometer per hour only. So we are not indulging any kind of certification at all. And further, this is another model developed by our student. So these are the few things we are already doing. My students are already doing. I am just as a mentor for them. This is something test tried earlier around. So these are few publications from our lab. This is an old slide actually. We have not included the recent one. So thank you very much from my side. Now I have a full time for your questions and answers. So now please, I'm open to your questions and answers. Please.
So participants, if you have any questions. Yes, participants.
Am I audible?
Yes, sir. You're audible, sir.
Sir, it was a great pleasure to listen to you. And especially on the research area, your students that you are working. You are really taking a lot of efforts in the that you have presented right now. And the fundings that have been received from the different sources, that those fundings are also going to motivate the students as well as your institute to work in those particular domain. But being from a private institutes, there are a lot of limitations that we are facing when we are asking for the funding from different platforms. So the private institutes like our institutes are facing such issues. But then also we found a lot of different small areas where our student can start the projects, so that it can be a day that the big funds can be received by the private institutes. About the smart grid zone, so this particular domain of the smart grid is obviously upcoming domain, because when you talk about the frequency changing, and when you talk about renewable energy, and when electrical vehicles will be coming, and vehicle to grid and grid to vehicle, this scenario is going to happen. These all domains are actually the research domains. Uh, but you try to explain it very properly. And as on today, there are a lot of n number of questions on different platforms that are supposed to be discussed. So it will be very good that if you share your email ID. So for any queries, we can ask the questions to you. Because at right this time, there are a lot of questions which can be asked, but it will be better if you share your email ID, sir.
Already I'm sharing in my chat box. Okay, the chat box of this talk, I'm sharing my email ID.
Sir, it was great to listen to you, because the way
I've shared my email ID, and if you visit the page also, you will find that somewhere you will find contact number also. Okay, so better to communicate on email. That would be nice. And if something is urgent, we can talk on phone also. And one thing you talk about the funding in private institute. Basically, see, if I say the same thing for IITs, how you will react? Actually, in last 2019, I think it was September, I was in IIT Suratkal for some talk or something. I didn't remember exactly. I think to attend some seminar or something, I was there. So, DRDO chairman, Dr. G. Satish Reddy, even in 2018, we host him also. So he was there, and he simply told that if you are writing any proposal to DRDO, then he told that we never differentiate between IIT or NIT or any government institute or private institute. We see the quality of the proposal and the strength of the implementing people, who are the strength of the team.
Okay.
And simply we act on this.
Okay.
And everybody knows that we have a lot of people in a even private segment, also in government colleges, in NIT, and they are even working better. Okay, even IIT people also accept this, that few people in NITs or in government college, they are working better than even IIT people also. This is also true. Okay, so even recent example, if you know Professor H.M. Suryavanshi from VNIT Nagpur, he is my guru. Even I consider him as a mentor. He recently become IEEE fellow. Okay, and I know many people who are stalwart in their field in the IIT. A lot of IITs, they even didn't become the fellow.
Yes.
So never think in that direction. If you have a actual concept or actual input or actual quality in that work, definitely people are there to grace you. Okay, and I agree that there's some issues, there's some lobby or something, but it happens, not an issue. Okay, so but we should always try. See, if we won't try, we won't reach anywhere. If we won't try, we have curtailed our chances in the beginning itself. Okay, so first thing is we should try. We should try, then we have chance.
Thank you for your motivational words. Because
even for this EU, recently there was a EU grant, European Union grant. Okay, and there are only 3 grants to be won by the participant. So I think ISC Bangalore, IIT Mumbai, IIT Guwahati, IIT Delhi, so lot of people are a group, basically a group of at least 10 to 15 professors in a one grant. Okay, they are applying. So 20 such group has applied. 20 such group have already applied by collaborating with European Union countries, UK, Norway, Bulgaria, so many countries are there. Okay, 20 are there. We have also participated in that. If we thought that they are big short ISCs, IITs, they are participating in that where we have our chance, then we have out in the beginning itself. But right now we have a hope that we are in the contest. Okay, even when we started as a NIT, lot of IITs came together with us that okay, we are also partner of your, I mean, like just like that. Okay, so means need to try. If we lose also, we won't lost anything. We will have an experience to tell. Okay, so just
Thank you
like
for your good words.
we have
Thank
to try. Simple.
It will recently, it is obviously going to motivate us for putting a good proposals. Thank you.
Thank you.
Sir, there is one more question in the chat box, sir.
Yeah, I'll go to the chat box. Okay. How recycling of batteries can be done in an eco-friendly manner? That is basically the area of waste management. People who are working in this area of waste management, those people know better how to manage this e-waste of electronics and all those things. Okay, so this is basically some startup should come in that direction, that how to recycle the things, how to recycle, or by recycling how to make another material or something like that. Okay, so not for the electrical people, but people who are working in the area of waste management, they can take up this call. So if you have any question, please let me know.
Yes, participants, still, do you have any questions? Or sir has shared his mail ID in the chat box, so you can also communicate with him on the mail ID also.